I totally just glossed over it. And so it is worth you seeing. It'll take me about, I don't know, 3 minutes to show you. It is worth it. So here, where does the torque formula come from? Let me do that for you real quick. Again, here's my current loop, looks something like this. Let me say on the plane of the paper, magnetic field points down. And let me say that my loop, it has dimension L1 and L2. So let me say those are my two dimensions. And let me draw it from the edge view here. So look kind of something like this. You won't be able to see both sides, but it is L1 here and L2 here. And the normal vector is going to go like this. So let me draw this here from the side view. It's going to look something like this. Current's going to come out. Current's going to go across. Current's going to go in. And we've already talked about, let's see, we said L1 is here. L2 is kind of not visible. It's kind of going in, it's kind of in this dimension here. So this is L1, this is L2, L2 here. So let's go ahead and figure this out. We've already, from the previous video, know that the forces are the relevant forces are going to point like this. That's where the torques come from. To get the torque, we just use your favorite formula from Physics 1, T equals RF sine theta. Again, there are many ways to express this. You may have seen equals LF. Depending on who you had, you may have even seen the full cross product form. But this is my favorite, so I'll use that. So first of all, R is the distance from the pivot to where the force is applied. It's basically kind of like your leverage. If something's just kind of free floating in space, then the default pivot will be the center of mass, which is right in the middle here. And so the distance from that to where the force is being applied here is this distance right here, which is L1 over 2. And then the force, of course, is a magnetic force. So FB, I'll just go ahead and put in ILB sine of theta from the previous page. And this L, that's of course this other L, this L, right? This is the side being pulled on, so that's L2. The angle between I2 and B, you can see that this current is always going to be 90 degrees to this magnetic field. Even as it rotates, it's going to stay, that side is going to stay perpendicular to the field, okay? So that angle is 90. And then the angle in the torque formula, this is to make sure that you're not accidentally counting any radial force, you're just wanting tangential force that's helping you. The way that you get it, this is how I like to do it. I draw a dotted line from the pivot through the force application point, and there's your theta. So sine of theta. And that's pretty much it. Let's see what we got so far. Let's see. I guess I'll write it like this. I, L1, L2, B, sine of theta over 2. And let me get rid of that 2 real quick, because of course I have 2 of these forces and they're both basically reinforcing the rotation. So if I want to get the overall, I have both forces accounted for just by going like that. Let me note that the area of the loop is L1 times L2, right? Length times other dimension. I don't know why I added an I1 here, so that doesn't need to be there. And then B, and then this theta is actually, if I go ahead and I draw in my my dipole vector points like this, and my magnetic field points like this, just copying it from over here, and if you don't see it right away, you can convince yourself that those are the same angle. So this angle is going to be the angle between M and B. And then looking at this, it's pretty much the same deal as what I already got. Just if I have a bunch of these loops stacked on top of each other, then they'll all get torqued. So I can multiply by n. And of course this right here is my magnitude of my dipole vector. And boom, I have now rederived that formula. You might ask if this is worth doing. Well, I'm going to do another torque calculation in a little bit and kind of use the same techniques. The other thing you might ask is that can you use this on any loop you want, even if that loop is not rectangular? Yeah, you can. I certainly did it with a rectangular loop because it's easier to derive. And the area here is L1 times L2. But even if you have any kind of crazy shaped current loop, you can always split up into these little segments. And it turns out that you essentially can count the sum of the segments going into the leverage part, the sum of the segments going into the force part, and it works out exactly the same. So if someone gives you that the current loop is a circle, just use pi r squared. And if someone gives you some crazy shaped loop like this, you can literally just use whatever the surface area of that is in your calculation. You don't have to have it be a rectangle, even though I found it convenient to derive it that way. Okay, so at this point, the one thing we do need to introduce is the energy of a dipole, the potential energy. So this is something that is not mentioned at all in the previous video, so let's talk about how we do this. We can pretty much follow the same prescription we've been using for finding potential energy, or voltages, which is just the closely related quantity that we've been doing all semester. So let me remind you roughly how this goes. So we've been integrating up from knowing the force, or of course what we've been more typically doing is integrating up the electric field to get to the voltage. That's just if you multiply this whole formula by charge, of course, that becomes this. So this becomes Q times delta V is delta U, and over here Q times E is the force. So either way. So let me go ahead and do that with a dipole. So the only problem, of course, is that the whole system is rotational. So let me go ahead and just replace the rotational version of force as torque. And instead of changing by a small distance, I'm going to change the dipole by a small angle. Okay? So there's my rotational version. So here's let's say my magnetic field points like this, downward. So that would be the preferred orientation of the dipole. So that would be where it experiences zero torque. That's your stable equilibrium. But let me, for instance, start from some random angle, theta initial, and let me lift this thing up to some random final angle. I guess I can draw it anywhere, but let me draw it here. So I'm going to lift it up to some larger final angle. Okay. So here's what the calculation looks like. I guess let me call the final angle, let me just call it some random angle theta. So delta U is going to be the difference between the potential energy at my final angle minus where I started. And that'll be minus, and then here I have to be careful because I am lifting it to a larger angle, so my change in angle is increasing, but my torque is actually fighting me. It's of course the torque wants to bring it back, so if I'm going to a larger angle, I'm going against the torque. The torque wants to go down to make this angle zero. So this dot product is going to yield a negative sign, right, when two things are pointing opposite. So this is going to be minus the magnitude of the torque, d theta, and those two minuses wipe each other out. And then of course the magnitude of the torque, mb sine theta. So that's mb sine theta, and m isn't changing, the magnitude of my dipole vector, the field isn't changing. The only thing that is changing is the angle. I'm making the dipole have a different angle inside the field. And so I go theta initial to whatever theta over here. Integral of sine is negative cosine. Negative cosine of theta. And then I evaluate it, theta initial to theta. And let's pull that minus sign out front. Cosine of theta minus cosine of theta initial. And then, if I want to find a formula for the potential energy, I go ahead and let me go ahead and write this out over here. And then I, of course, need to throw this on the other side. So there is my formula. So we've been in this position many times before, most notably we were coming up with original potential energy functions for point charges at the beginning of the class, and especially in homework number 4 when you're doing your integrations of your piecewise electric fields with Gauss's law and you had to make decisions on how to stitch the voltages together. So I'm going to try to wipe out as much of this as I can, and I can do that. I'm looking at this, what initial angle would make this 0? So of course the angle that would make this 0 is actually 90 degrees, cosine of 90 is 0. And then I'm going to choose that at 90 degrees, I'm going to choose that my potential energy is 0. And so what that does, it leaves me with this formula, which, looking at it, conspicuously appears to be a dot product. So all the properties of a dot product, right? Two vectors walk in. These are both vectors. Their magnitude times the cosine of the angle between them results in a number, right? So that's what a dot product is, right? We have a vector, and a number walks out. And the number is proportional to the cosine of the angle between them. So that is a very straightforward formula I can use for the dot product. However, it definitely is worth doubling back and saying, wait, what? We chose the potential energy to be 0 at 90 degrees? That's a really weird angle. You would think that you would choose the potential energy to be 0 down here, but we haven't, okay? Now, as much as that might seem crazy, I do want to show you that it makes a lot of sense. And I want to show you why that makes sense using the pendulum again. So draw a pendulum. There's this lowest point. There it is at 90 degrees, and a pendulum could even be sitting up here. If it had a rigid rod, then it could stay right there, or it could exist right there. And we've already talked about that this is a torque of 0. This is a stable equilibrium. This is a torque of 0, but it's highly unstable. Of course, a pendulum won't stay up there. If there's even the tiniest little breeze, it'll blow it off of there. It could only theoretically balance there if it was perfectly set up. And then over here, the torque was maximum. Now, in physics 1, let's say that this is m. This is the pendulum bob of mass m, and let me say that the pendulum has a length of L. Okay. Now, in physics 1, you guys are trained to usually set u equals 0 at the lowest height of interest. Okay. So you might say u equals 0 down there, and then of course you'd use your gravity is mgh to find it at the other places. So over here, of course, your height, well, now that mass is L above the bottom, so you'd use mg times L. And then up here, of course, now that mass is 2L above the bottom, so you might use the potential energy mgh, and now h is 2L. Now, there's nothing wrong with that. However, I might suggest the following. In physics 1, we're deathly afraid of negative potential energies, so that's why you always set the lowest to be 0, the lowest possible. However, what if I use this exact same idea, but instead I just go ahead and set u equals 0 here, where the pendulum made a 90-degree angle to the ground, or to the vertical. And if I did that, my height up here would be plus L. So this would be plus mg times plus L. And down here, my height, well, I'm L below that, so that'd be mg times minus L. And so, if you're okay with this reference being here, so u equals 0 is not the lowest or the highest potential energy, it's in fact exactly the middle. But it makes a lot of sense because now the values of the potential energies are completely symmetric around that. If the potential energies are positive, you know that the pendulum is more sort of up. And if the potential energy is negative, you know it's something more where the angle of the pendulum is less than 90 from the vertical, right? So here the angles are greater than 90, and of course the largest angle would be 180. And then here, down here, the angle of the pendulums will be less than 90 and down to 0. So that's really all we're doing with this, this pendulum, right? When we're saying u equals minus m dot b, or u equals minus mb cosine of theta, okay? If we look at that, we go ahead and realize that if we draw the magnetic field as being downward, so we know that when the magnetic dipole points down like this, and that's the torque of 0 state, that's where it wants to be, it's perfectly stable there, and then over here, when it points 90 degrees to the field, and that, of course, is our maximum torque. And over here, when we have this strange anti-parallel, or the magnetic dipole pointing opposite the field, we call that, that's also our torque being 0, but it's unstable. We're really applying the same exact idea, okay? Because if you look, if we plug in here, when we're at theta equals 90, cosine of 90 is 0. And by the way, that was by design. We did that when we set up the original equation. So that is neither the highest nor the lowest potential energy of the dipole. The 0 is, the reference is set right in the middle. And then over here, looking at the formula, if we plug in, so I guess I should write out here, this will give us 0. If we plug in cosine of 0 degrees, because the dipole is aligned with the field, we'll get minus mb. So that is minus mb. That is actually the minimum. That's the smallest value you could have. And over here, when we plug in that the dipole is 180 degrees to the field, well, cosine of 180 is negative 1, cancel by that one, so we get plus mb. So this is actually the maximum potential energy. So you can see it works exactly the same way. The u equals 0 reference is not the highest potential energy, it's not the lowest, but it is halfway between the highest and the lowest. The maximum value, which is positive, is up here, and the minimum is down here. And by the way, this goes and immediately explains why is this equilibrium unstable and why this one is stable. Because we of course know that systems want to go, all systems seek lowest potential energy possible. So this might be stuck here if it's perfectly balanced, but if you poke it even slightly, it does not want to go back to a higher potential energy, it wants to seek this one. So that's why this is going to flop over and want to seek this one. It's unstable. And at the same time, this one is stable because this is the lowest potential energy possible for this particular system. Dipoles want to align with the field because that is the lowest potential energy state. And if you poke it a little bit, of course, it wants to come back. So that makes it a stable equilibrium. So hopefully this pendulum analogy really helps you. And the idea here is that while we do have a very weird reference for the potential energy, U equals 0 is not the highest, it's not the lowest, but potential energies in this range are positive. That's when the dipole more points against the field, and when the dipole more points more with the field, you'll get negatives. You can kind of think of this formula right here. This quantity right here, of course, this is that maximum potential energy. So another way to think of this formula is like this, okay?